All right, okay. Thank you very much for coming to this section. I think this is the last paper presentation section of today, right? So, welcome. The section is for MPC for General Functionalities 2. So we have three papers in this section. I think the first paper is on the wiki reverse multiplication friendly embedding constructions and applications. And the speaker will be Yun Chen. So let's welcome the speaker.
Thanks for the chair's introduction. And this paper is a joint work with Daniel Escudo, Hong Chen, Liu Hongqing, Xing Chaoping. Yeah, I will start the talk. Okay, so first I want to introduce the MPC. So what is the secure multi-party computation? Usually, if without MPC and if there are three players or maybe five parties, and they have the private input x1, x2, and x3, and they can obviously they can send this their private input into a server, and the server will compute a public function f based on x1, x2, and x3, and then return the results. And this is a centralized computation. Uh, okay. However, if the server is an adversary or corrupted, and you cannot send your private input to the server or to the server, otherwise, and your private input will be leaked, and it's not secure. And instead, maybe someone can think we can do it without the server. Yeah, we can do that like the distributed computation, and that's doable. However, you don't know if one of the party or any of the party is corrupted or not. So if some of them is corrupted, okay, and then if you do the distributed computation, and it still can your private input is still not secure, and due to this corrupted party. So that's why, and we may need some secure multi-party computation, and it's just in the presence of some corrupted party, and the computation itself is still secure, and so your private input will not be corrupt be known by the adversary. So this is the idea of secure multi-party computation. Okay, in secure multi-party computation, actually, so in this case, we can see there are four parties. Actually, you can think of it as many parties, and they do a MPC protocol, and this protocol is over F2 to the K. Why? And usually we think the K is quite big. Why? And there are two reasons. The first reason is for dissonant majority, and if the K is bigger, it means that the RC will be caught with high probability, because the error probability usually is inverse of this field size. And the second reason is that for threshold almost majority MPC protocol, usually we use the Shamir secret sharing for the secret distribution. This Shamir secret share scheme, and it's so it has some constraint, like the player number is at least is at most the field size. So in this case, if we have n parties, and the field size should be at least n. And this will also, I mean, if you compute some message, the message itself is over a small field, but you needed to embed it into a big field extension, the field extension of this field, so that you can make this whole protocol work out. So the question is, can we achieve the same performance for any field? Actually, it's doable. In 2018, we also with Ronald Grammar and Nacho and Xin Chaoping, and we introduced this IMFE technique to amortize combination complexity, and the Grammar, Rambert, and Xin further extended it to integer rings instead of the field, and show that they can be as efficient as its counterpart over field. And I just want to introduce the idea of this IMFE. So what is IMFE? Here I use this integer ring version, not the field version. So here we have two linear P to the K linear maps. Also, sorry. Okay, it should be Z2 to the K, and the P to the K is also doable, and here's a typo. So it's phi is from Z to the Km, and it's m-dimensional, mapped to a Galois ring. Galois ring is, we can think of it as the extension, as the field and extension field, the counterpart or version of a field and extension field. Basically, it says that we use the f to d to the k and x divide some polynomial of irreducible polynomial of degree d, then you will get Galois ring. And then we have another maps and just do the inverse map. And so for any two vectors and the component-wise product equals to, we first map it to the Galois ring as an element, and then do the multiplication and map it back. And these are the same. Okay, you get the same results. And also we may need to calculate the ratio. And the ratio means that because we embed some vector into a big Galois rings, and they will have some loss. And the loss is roughly 4.9. And so the idea is like, so now we can use the field, the element over a large field to do the MPC protocol, and then run the MPC protocol, then obtain the result, and when we map it back, and actually we got the component-wise product of vectors over some integer ring, and this nice property allow us to simultaneously calculate multiple instances. Okay, so now we can see this application of RMFE. Actually, now here I will just illustrate this example with 4 parties. First, the 4 parties, each of them has maybe D private input. You can think of it as D instance. And then the first step is that they map it to here I use field for the example. Actually, it also works for the integer ring. Then they map it to the k and to an element over an extension ring, extension field. Okay, so because we have this MPC protocol over large field, and we run it with this input by x1, by x2, by x3, by x4, and then we got output is f by x1, x to the x4, and then we mapped it back, use the psi, and then we got d multiple instance, d instance, and each instance correspond to the one output x1, x2, x3, x4. And then actually, so we run once this MPC protocol, actually we got the output, and you think of it as the instance. Okay, so the previous work on RMFE only supports the multiplication of 2 elements. Actually, so this is the MPC protocol, but we need, because we need a Beaver triple, and one Beaver triple only involves the product of 2 elements. And actually, so we generalize RMFE to degree D RMFE, which supports multiplication of D elements. This is the idea of how this works. Okay, so let's see the definition of D MFE compared to the degree 2 MFE. Actually, we support D multiplication. So here, and we have D elements, D vectors, and the component-wise product of the elements, and equals to the same thing, but actually we have the 4 D elements instead of 2. Okay. So here I just want to give you some instantiation of degree D RMFE. Actually, it's quite it's not unimaginable actually. So we can first we use this polynomial evaluation to instantiate this degree D RMFE. Okay, so to make it simpler, I just assume that our map is from FP to the K and to the so the small space is FP to the K, and this is vector space, and the extension field is FP D times K minus 1 plus 1, and so psi is just the inverse map. Okay, so so how to construct this phi and the psi? Here, and I give you just an example. So let alpha 1 to alpha k be k distinct elements in P. So for any vector a1 to ak, this is one vector, and we can find a unique polynomial of degree at most k minus 1. So satisfy f alpha I equals ai. So this is just a polynomial interpolation. And we can treat this extension field as fp to the x divide some hx. The idea of hx generated by hx is just some degree or irreducible polynomial of degree d times k minus 1 plus 1. So then we just the phi just map a1 to the ak to fx. Yeah, because here we don't use the extension field, but use this this representation. So then we cite just the maps gx to GA1 to GAK, because each element in FP in this extension field is we can think of as a polynomial. So we use polynomial evaluation to do the mapping back. Okay, so then we just consider the multiplication. So how the multiplication works out, and for any d vectors x1 to xk, and we first do the interpolation and provide and obtain the f1 to the fd d polynomial, and for this d polynomial, and we know that fi xi equals fi x. So this d multiplication, component-wise multiplication, and we can think of it as fi a1, and this is a product of d polynomials at evaluation at a1, at a2, and at ak. So there we map it to f1x to the fpx. Then, and because this psi is just an evaluation, so we just then we map it back to the, and then these are equal. Okay. So the key idea is that this f1 to this polynomial f1 product of f1 to the fd is a polynomial of degree at most d minus 1 times k. So this is just it's unique, and because of this field is quite big enough, so it can this map is just the injective map. Actually, it's not a bijection actually. Okay, so this is a very simple instantiation of degree d MFE. Okay, so actually, so the downside of this IMFE, if we look at it, it still requires polynomial, and the polynomial, because we don't know if we have enough points, because we require alpha 1 to alpha k are distinct. If p is small enough, we cannot find so many alpha I. So this construction doesn't work out in this case. Okay, so here we will introduce the composition of IMFE. If we have two IMFE and over different fields, and the first one is over some small field, and another one is over some big field, and we can have a composition of these two IMFE, and these two IMFE will start from small field to a very big field. And so in this case, we don't. So even if we have some constraint on Q, and then we still can increase the size of Q. You still can increase the size of K1 and K2, and so this will make life easier. And okay, this lemma allows to let K tend to infinity, and here is K1, K2. Actually, if we can do it recursively, and then it will goes asymptotically. The ratio, and the ratio of this composition is K1, K2 over N1, N2. Okay. Okay. So in our construction, and we have to rely on some algebraic geometry code to obtain asymptotic good degree D MFE. So if we do the combination and we do this composition for polynomial codes, we will find that the ratio will tend to 0, because we need log and the ratio actually is log n 1 over something like this, and so it goes to 0. If we want some asymptotically constant ratio, and then we must rely on some algebraic geometry code, and this construction is obtained by composing 3 3D MFE, and one of which is derived from algebraic geometry code, and the ratio is roughly this one, this result. You can check it. Actually, in our paper, we provide several constructions, and each construction has their own advantage. Someone is better in smaller size, and someone is better than large size. So maybe you can check it in our paper. Right. So maybe next I want to introduce some homomorphic encryption, which relate to our IMFE application. So in here, I don't want to introduce the whole picture of the homomorphic encryption. I just want you know that in somewhat homomorphic encryption, the plain text is of this form, and ZQX divides some m cyclotonic polynomial. And usually if Q is prime number, actually and this field could be splittable, and the phi mx usually is splittable, and it can split into the product of a linear polynomial. However, if Q is 2 to the k as the 2 prime, prime power, and it's not splittable. And usually we will write phi mx as f1x times ftx. Each one is an irreducible polynomial. Okay, so here because of this representation, and we see that it is equals to this. This is just for CRT Chinese remainder theorem, and we can write it in this form. And each one is like a Galois ring. Actually, this is a Galois ring. If f1x is a degree, the degree of f1x, f2x is larger than 1. Actually, this is the representation of Galois ring. Okay, the common equation was used in a variety of speech protocols to prepare the correlated randomness for the online phase. And the idea is just to embed the message into the context of homomorphic encryption. And Chen and Li proposed a unified framework called packing method. And actually, the packing method is quite similar to our MFE. Actually, they also say that our MFE is not exactly the packing method, but they can use the packing method, the lower bound, to bound our MFE's lower bound. And the packing method is actually a mapping that it's one mapping from Galois ring and for small Galois ring, and another mapping for a big Galois ring, and the extension of this Galois ring. And one is just like a vector space, another one is like just like the Galois ring. So the packing is maps the vector into a Galois ring, and the unpacking is mapped back from the Galois ring to the vector space. And so they support this is a linear. This unpack over the linear, and so it supports the multiplication. So you can think of it as it supports the degree D multiplication. And so for if we multiply D vectors together, and then we just map it, and we will get the desired result. This is the idea of this packing method. Okay, in our paper, and we just show that if the packing method is linear and it's equivalent to the definition of degree IMFE, and then the construction of IMFE can be applied to the packing method, and then we just provide some comparison. In our work, the packing density is in 3 over d times roughly d 2 to the 2 times d square, and in their paper, and they provide another construction. Actually, they are tweaked packing method. It's not exactly the RMFE, but here is their k divided over d times k plus d. K is the packing method over the c to the k, and the d is at least d, which is the degree of irreducible polynomial. And if d is big enough and k is small, actually our bound is better than theirs because we are independent of k and d. And the overdrive, actually this ratio goes to 0, so it's not good enough. And also it's only applicable to d is equals 2. Okay, so then, and we also in our paper, we consider the application to MPC protocol for our degree D MFE. And we consider application to MPC where the high degree computation is required. The interaction is less desired. And actually there are 2 committees instead of usually MPC computation, you have 1 committee. Because these 2 committees, one is processing committee, which is required to generate the correlations, and the online committee is consume these correlations to securely compute the desired functionality on their private inputs. So actually, you can think of this outsourcing computation, and the per processing committee is some server. So here we introduce this degree D correlation, and the degree D correlation is okay. Think of it like we have this multi-polynomial f. F has n polynomial n inputs, and its output is just y1 to yn. Each one is over zq. So yi is just you can think of yi is like a multi-variety polynomials, and fi and with n variables. And so f we must bound the degree of f. So the total degree of f is at most d. So this is called degree D correlation. So there's a very simple example is a Beaver triple. In Beaver triple, actually we got y1 equals x1, y2 equals x2, and y3 equals x1 times x2. So it's a degree 2 multivariate polynomials functions. Actually, you can think of it as this. So this degree D correlation is generalized this Beaver triple idea. Actually. Okay. So for we just introduce how to generate correlations, and from this degree D correlation polynomial, and all party and in pre-processing set pre-processing step, and all parties in P just generate a sequential scheme is x1 to the xn. Then all parties in P securely compute y1 to the yn based on x1 to the xn. We note that because this is a degree D multivariate polynomial, so if we are sequential scheme and if we allow the degree to go bigger, and actually we can do it locally, and we don't need to any interaction to do this one. And then we just share y1 to yn to each party, enable parties in Q to generate their shares y1 to the yn. This is just the idea of how to generate the correlations here. Okay, the challenge is that okay, so the Sherman sequential scheme have very small length of fz to the k. Because in z to the k, it's just like f2 to the k, you have 2 to the k points. In this z to the k, you only have 2 points. So if you do the Sherman sequential scheme, you only got 2 points. So we have to use the Galois to increase the length, because in Galois we consider extension field, and we have more points to interpolation, so we can make the degree higher. Okay, so then we just compute this input. We have input x1 to the xn. It's just a vector space. It's a vectors instead of an element, and then we use the MFE to map it to a Galois ring, which is bigger, and then we generate the sequential ring schemes. Yeah, based on this phi x1 to the phi xn, this input. And then we generate the correlations according to the previous according to our previous slide, and we got this phi1 to the phi n. So we know that the degree will grows higher because this function f is a degree D correlation. So we increase the Sherman sequential schemes in this case, and then we apply MFE again to map it back to a vector. And then we get this FI, we got these correlations, and for k correlations. And so this is just idea of how to apply MFE in this correlation generation. Okay, so and then we just so to avoid the interaction in the offline phase, and we still do random sequential schemes to generate the Sherman sequential scheme. It's quite a standard process in the non-interactive sequential non-interactive MPC protocol. So here I just omitted this part because, and then the amortized communication complexity per correlation is roughly n d square n square, and n is the number of online parties. D square is the degree D correlation cost, and n, the small n, is the number of parties in the offline phase. Okay, so such correlation can save roughly d minus 2 rounds communication in the online phase, because instead of pure triple, we use the degree D correlation. It's to save the connect. Yeah. Okay. Thank you for your attention.
So any question from the audience? Let me ask you one question. So seems like from your presentation, is it the extension from 2 element to degree D is not very tricky? It seems like the only tricky part is the use the composition right method. Is that correct? Or there are other tricky part that we cannot understand?
Yeah, there are some details. I just omit some details. Actually, if you look at this degree D polynomials, so if we do this, apply this IMF, actually it's not the element. I mean, just you can map it to every element in this field. Usually, actually, if with malicious, if the diversity is malicious, actually we need to do some check to do if this map is correctly mapped. You apply the map correctly, otherwise the adversary may take advantage of it. Yeah.
Okay, so let's thank the speaker again. Our second paper is adaptive distributional security for governing scheme with order X online complexity, and our speaker is from Finland, Kurt Watson. Let's welcome the speaker.
So hello everyone, I am Kippy, and today I'll be presenting joint work with my fantastic colleagues, Eduardo, Chris, and Sabina. This work is about the adaptive security of gambling schemes with low online complexity. So let's briefly recall MPC. We have two parties, and uh, let's call them Eva and Gabriel. And Gabriel holds a circuit with their input hard-coded into the circuit, and they would like to jointly compute this function which the circuit implements, but Eva only picks their input later after they've seen the circuit. So Gabriel gabbles the circuit. That's just a way to take a Boolean circuit and to encode it somehow and hide the circuit. Sends it over to Eva, the evaluator, and then adaptively Eva chooses an input X. And Gabriel provides the gabbled input via an oblivious transfer protocol so that the privacy of Eva is preserved and the gabbler does not have to reveal the secret information used in producing the gabbled circuit. All right, so now the evaluator gets all the information it needs in order to compute the function. Now, one might ask the question, how do you define the security of an adaptive gabbling scheme? And one natural notion, which was first introduced by Galare, Huang, and Rockaway, is the adaptive simulation security notion. And this notion says that you allow the adversary to first pick the circuit, the entire circuit, unlike what we saw in the protocol. And then the adversary adaptively chooses the input and gets the gabbled input from that. This is called the honest gabbling. And the way we formalize security is we say that this game on the left is indistinguishable from this ideal game that is simulated. The simulator only gets some leakage of the circuit instead of the entire circuit. Think of this leakage as just the public part of the circuit failure without the hard-coded input. Or you can think of it as the topology of the circuit, if you know what it is. Simulator then returns the gabbled circuit. The adversary chooses the input, but now simulator does not get the input, it only gets the output of the circuit when evaluated on the input. And knowing the output alone, it needs to produce a gabbled input. All right. Now, size of the gabbled input is called the online complexity. And we want the online complexity to be short. What does that mean? We mean that it should grow in the size of the input, the size of the input, and not anything else. Why is this requirement crucial? Well, if we allowed the online complexity to be any size, then we could just ignore the offline phase and send the gabbled circuit in the online phase, right? We could pick a gabbled input and circuit pair, send it in the online phase. And that would grow in the order of the circuit, and we don't want that. So we want short online complexity. But unfortunately, this is not achievable under the SIM notion. So Applebaum, Ishai, Kushi-Levitz, and Waters, or AIKW, showed that in general, SIM requires online complexity that grows with the input length and the output length. And you can't really get rid of this dependency on the output length. And then later, Hubacek-Wicks showed that any pseudo-random circuit, like a PRF or a PID, is going to have this dependency on the output length if you want to define MPC in this like simulation. All right. So how can we get short gabbled inputs? Well, we have to consider different notions now. And one other notion that BHR introduced was this indistinguishability notion. And that notion involves the adversary choosing two circuits, and the gambler gobbles either the left or the right circuit, and then the adversary chooses an input and analogous to the gambler gives the left or the right input goblet. Now, the problem with indistinguishability is it has a really strong requirement. It requires that the left circuit, when evaluated on the left input, is exactly the same as the right circuit evaluated with the right input. Why is this a problem? Well, we wanted a new notion that bypassed the lower bound that came with simulation. That is, we want to gather these cryptographic circuits, and we couldn't do that with SIM. And this requirement that cryptographic circuits, when run on distinct inputs, output the same thing, is a bit too strong because it rules out most of cryptography, except for functional cryptography, which we don't know many examples of. So, the main research question is, can we define a notion that bypasses SIM and yet is not as weak as IN and is suitable for gathering cryptography with long outputs? And our idea is maybe we need to limit what the adversary can do. We don't want the adversary to choose the entire circuit and the entire input. And this is also known as a distributional approach. And it's not strange, and it has been used successfully in defining other things like deterministic public key encryption. Here you can't really allow the adversary to choose the entire message because CPA cannot be deterministic. And secondly, it's been used also in defining distributional zero knowledge, where instead of having any old statement, you have a sampler sampling a random statement. Okay, so let's actually look at the definition. And I want to do this by modifying the old SIM definition. So this was the old one. Instead of letting Ava choose the circuit, we don't allow that, and instead it comes from the sampler. The sampler produces a circuit, a linkage, and an oracle. And I hope you can see this. But think of the circuit as holding, having a public part, which is the linkage, and a secret part, which is the key. And the circuit is cryptographic in a strong sense. That is, if this secret part K is unknown, then any efficient adversary and for any input, these two distributions are indistinguishable. So indistinguishable from just zeros, for example. The circuit evaluated in zeros. All right. I also wanted to say something about the oracle. The oracle is something that models the kind of cryptographic guarantee that the circuit provides. And later in the example, you'll pick up here what it means. So we replace things now with things that come out of the sampler. And notice that unlike the old definition, we now give the same information to both the simulator and the adversary. So we've made things more fair and hopefully more achievable, and all parties get access to this oracle. And now we need to think about what we give the simulator when it needs to produce a guarantee. And we make this flexible. So in the case of SIM, you needed to have the exact same output. The simulator needed to produce that. But we don't always need this. So if the circuit we're governing has some pseudo-random guarantee, then the simulator doesn't even have to get anything. It just needs to produce outputs that are indistinguishable from truly random. All right. So that's the definition. So now I want to show you an example of using this definition to an application. And the application is so-called distributed symmetric encryption. Caveat, this is not the best way to do this, but it just shows you that this is useful for things like this. So the goal is we want to store some encrypted information, data M, on a database that we don't own, and we want to encrypt it under some key K, but we keep the key K on the server, or if the server gets corrupted, that's bad. So easy solution is we secret share the key into two servers and hope that not all servers get corrupted. So this is done in some setup phase, and recall the goal. It's to store the encryption of K, of M under K. And let's abstract the goal out. Now, this is the circuit, since we're going to use this in the gabbling, and this is the circuit that the gabbling party gabbles. And this has the key share hard-coded into the circuit. Sends it over to the evaluator. And then the evaluator later in some future online phase requests for all of those missing things it needs in order to compute an encryption. How do we prove the security of this thing? Well, now we've given both parties Oracle access to the end. And you can think of as the security guarantee of the encryption circuit. Say it provides eCPA security, and so it gives encryptions under the key tape. Now we see quite obviously how we can apply DSIM. We just replace this honest gabbling with the simulated gabbling. And here, the leakage is just the public encryption algorithm. And that's all. The intuition here is just that the evaluator does not learn much more than it would have just interacting with the end protocol alone. So these are not the only things that we look at in this paper. The paper has some other quite interesting results, which I would encourage you to look at. So we'll look at the definition and then application. But we also have a bootstrapping result. So we show that if you can construct DSIM for constant depth circuits, you can also get DSIM for arbitrary polysize. And the idea here is that you can represent the circuit you want to gabble as a randomized encoding. And that's just for those of you who don't know what randomized encodings are, think of a Gauss gabbling scheme as a randomized encoding. So any projective selectively secure gabbling scheme with it. So you take the circuit, you represent it as a randomized encoding, and that thing is in low, it's in constant depth. You gabble that instant. But you need to reduce to the kind of the security of the randomized encoding, and DSIM is perfect for that because you can hide whatever secret information or randomness used in generating the randomized encoding. All right. Next result was the improved a construction for indistinguishability security. This was a construction by Jaffa Golis Gafuro Wicks, and we showed that you actually can remove this dependency in the depth of the circuit. So you can get online complexity that only goes with the interface. And yeah, if I'm not mistaken, this is for NC1 circuits only. The last result is we improved the analysis of Huber-Check tweaks. They show a lower bound on the online complexity for any MPC protocol, but we show that we can improve the lower bound by a single bit for gathering schemes. And this is nice because all it requires to make this argument is simple counting. Here are some open questions I'd like to leave. The first thing is, obvious one is, can we construct DSIM? And even for constant depth circuits. Second question is, can you apply DSIM to something apart from MPC? I don't know, maybe functional encryption or something. That's all, and thank you for listening.
Thanks for the talk. Question from the audience. Yeah.
soccer. I'm wondering, this adaptive model can be extended to multi-party competition, because this is it seems to two-party competition.
True. I don't know much about that. So I know that there exist governing schemes for more than two parties. I don't know how you prove that.
As I know, multi-party computation based on coupled circuit is based on like a GCM, like it is sharing the input of the coupled because it's many coupled parties. So maybe the evaluator is also the adaptive adversary like yours. So maybe it's
Maybe. Yeah, figure out.
Thank you. Any other questions? Right, but on the other hand, do you know the security level gap between your notion and the original simulation notion?
Did you say security gap?
You have like whether your if I can prove the scheme secure under your DSIM.
I don't understand the question.
Okay.
So like
I see.
you mean the online complexity? Or
Right.
You mean the
because right now you only require the output to be the same instead of the circuit, right?
Yeah.
So does it affect the security of the application?
So did you say the output to be the same?
Yeah, I mean in your definition, right?
Yeah.
You require the output to be the same instead of the circuit, right? Check.
No, I mean
Okay.
you can, so it's flexible.
I see.
You can let it be equal, or you can also choose the outputs to be not have this requirement. That's the point of using PC. So you can have if you want to garble the pseudo-random function,
Okay.
the output doesn't have to be exactly the same. It can be just something that's indistinguishable from random. The reason we can do this is because we hide the key of the parent. We don't give the adversary this information. About the security loss, it depends on the assumption you use to construct your governing scheme. So if we have a construction cohesion, then we can compare it with non-construction.
Okay. All right. Okay, next vendor speaker. Oh, sorry, one more question.
So
Yeah.
who runs the sample algorithm in your definition? Because you said that there's a third party to run that.
You mean where it comes from?
Yeah, I mean,
So the sampler kind of comes from the sky in a way. So when you quantify over your adversaries, I mean, you can think of it as a separate adversary. So you say for all samplers and for all adversaries, there exists a simulator such that those two games are indistinguishable.
so in fact, it's basically another party and the adversary is enough to run it, or the same adversary can
In
run it?
our example, you can think of the sampler as the original server that happened in the setup phase.
Okay, so
Yeah.
basically, it's part of the setup phase.
Yeah,
Sampling, so
if you want to construct an MPC protocol,
that
yes.
requires to be trusted, I guess. Okay.
I mean, we are the people who set it up, and we want to protect the games. Artists who get the cobbles. Yeah.
Thank you.
Okay, let's find the speaker again. Right, comes to our last paper, MPC with related parties over Starlight networks, and the presenter is Mariana. Let's welcome the speaker.
So hello everyone, I will be talking about a new party computation protocol where we take into consideration two major constraints that are commonly found in deployed systems. And this is joint work with Emad, Emanuela, Nigel, and Paul. So MPC has already been defined in previous talks. Essentially, the goal is to allow a group of parties to compute a joint function over the inputs. And even if there is an adversary controlling some percentage of the parties, then this adversary shouldn't learn anything other than the final output. Now, when designing MPC protocols, there are a few very common assumptions that I would say are present in most of the protocols. And these assumptions, on the one hand, they help build efficient protocols, but they also make these protocols a bit unrealistic for many scenarios. And the first assumption is that there is a dedicated fast communication channel between each pair of parties. And so as the number of parties grows, this can quickly become unfeasible. Another assumption is that all the parties will stay online throughout the whole computation. So what usually happens is that if some party drops out for a while, either because they lack resources or some other reason, then the protocol will just abort and all the work that has been done is lost. So in this work, we try to build an MPC protocol where we don't have to make these assumptions so that we can have something that is a bit more in line with what happens in the real world. Okay, so I will start by giving sort of an overview of what we did. So the first thing is that instead of having this type of communication topology, we have something like this. So we have a star-like communication topology with a few relay nodes. And we need at least 2 relays, and I will explain later why, but it can be more. So essentially, each party only has to establish communication channels with these 2 relays. And the relays, they actually act as storage. So when I send a message, I send it to the relays, they store it, and then when the receiver is ready to receive the messages, then the receiver will just ask the relays for the message. And this is actually quite useful for the next point, which is that we allow parties to be delayed. So we are still in a synchronous network, which means that the protocol proceeds in rounds, but we allow parties to be delayed for up to a certain number of rounds. And these delays can be caused either because the party is just very slow doing the computations, or the parties can actually drop out for a few rounds. And whenever they come back, they can just catch up by asking the relays for the messages that were sent in the meantime. And the parties that are not delayed, so the faster parties, they can actually move ahead in the computation, so they don't have to always wait for the delayed parties. Okay, so there are a few other works that have a few of these characteristics. The work that is more similar to ours, I would say, is this white CT paper, where they also use relays. But here, the relays have to constantly run a consensus protocol to ensure that their state is consistent. And this is actually quite expensive. And in our work, we show that this is not needed. And then there are a few other differences. For example, the goal of their protocol is to do threshold CBSA signing, which is a small computation. So they don't really discuss how to minimize the states that are stored in the relays, which we do. And there are some other differences that I will mention now. Then there's also this work by Ben Hamuda et al., where there are no relays, but they also consider delays, and they also allow faster parties to move ahead in the computation. But here, the delays are a bit different from our work, and they have a maximum number of messages that can be delayed per round. Then also their multiplication protocol has a bit of extra overhead when compared to ours. Finally, there's a line of work on MPC with dynamic participation. One of these works is the Phoenix paper, where they also consider parties who drop out and then come back. But here, the parties that drop out are not assumed to be able to recover the messages that were sent while they were offline. And the way they go around this is by requiring that there's a certain number of parties that remains online from round to round. Okay, so now I will explain our protocol in some more detail and see how we combine the use of relays with also the possibility of parties being delayed or dropping out. And the first building block of our protocol is Shamir secret sharing. And with Shamir secret sharing, if I want to share a secret, I just need to sample a random polynomial p, where the evaluation of p at 0 is my secret. And the degree of this polynomial will tell us what is the maximum allowed number of corruptions. So if the degree is t, then we can allow at most t corrupted parties. But we also know that to do multiplication with Siu Ming, then we need to have a honest majority. So we need the total number of parties n to be at least 2t plus 1. And of course, if we want to allow the maximum number of corruptions possible, then we can set n exactly the same as 2t plus 1. But here we are actually interested in the strong honest majority setting, where n is strictly greater than 2t plus 1. And that's because this is what allows the faster parties to move ahead in the computation. So even if there's some parties that have delays, as long as we have 2t plus 1 parties that are ready to continue the computation, then they can move ahead. And later on, the delayed parties will catch up by requesting the messages from the relays that were sent in the meantime. So the next building block is the relays. And we can send two types of messages using relays. We can send point-to-point messages and broadcast messages. So I'll start with the point-to-point messages. And here I will assume that there has been some key agreement and parties have pairwise secret keys, but in the paper we discuss how to do this. So if party I wants to send a message to party J for round K, then this party will just use the exchanged keys to encrypt the message, and then we'll send the same ciphertext to both relays. The relays will store the ciphertext, and whenever party J is available, then party J requests the message from the relays. Now, party J will only accept the received messages if they both decrypt correctly and they decrypt to the same thing. And this is why we need more than one relay, is because we actually allow the relays to be corrupted. So even if there are corrupted relays, as long as there's at least one relay that is honest, then the party will detect any malicious behavior or any wrong messages that are sent by the relays. So this is point-to-point messages. We have a send command, a request command, and also an erase command. So whenever the parties don't need a message anymore to be in the relays, they can just say, and the relays maintain two counters, one counter for the received messages for each pair of parties, and also a counter for the deleted messages. Now, broadcast messages are actually almost exactly the same, except that because they are meant for everyone to see, we don't need to encrypt them. But other than that, everything is the same. So while usually we have that broadcast is more expensive than point-to-point communication, here, broadcast is actually slightly cheaper because we don't need to encrypt the messages. And this will be quite useful later on when we want to do multiplication protocols. Okay, so before I explain more details about the protocol, let's see the adversary that we want to protect against. So, because we are using Siu Ming secret sharing, the adversary can corrupt parties as long as there's a honest majority. The adversary can also corrupt relays as long as at least one relay remains honest. And the adversary can also delay an arbitrary number of parties for up to delta rounds. Okay, so what we present is a protocol, an MPC protocol that is passively secure against this adversary. However, we would like to have malicious security. And for that, what we do is that we look at some previous results that tell us that if we have passive security with additive attacks, which means that if the only thing that the adversary can do is introduce some additive errors, then we can actually compile our circuit to get additive active security with a bullet. And essentially the way that this is done is by running the same circuit twice, once with the original inputs and another time with a randomized version of the inputs. And I won't go into a lot of detail about this, but essentially these two circuits are then used to complete some checking iterations that will tell us if there was an additive error or not. And the way these checking iterations are computed is similar to what is done in fluid MPC paper, which is that instead of just computing them at the very end of the protocol, we compute them gradually throughout the operations so that the relays don't have to store a very large state. Okay, so what we want is to build an MPC protocol that is secure up to additive attacks. Now, we are using a linear secret sharing scheme, so linear operations can be done locally. So the place where the adversary can introduce these additive errors will be in the multiplication protocol. So we have to look at the multiplication protocol we are going to use. So first we consider the model multiplication protocol. So here the parties, they start by locally multiplying their shares, and then they have a secret sharing of the result, but it's a secret sharing of the degree 2t, so they want to reduce it to degree t. And for that, they reshare the results they got in step 1. However, there's a problem in this step, which is that when the parties do this resharing, they can introduce different additive errors for different groups of parties. So what happens is that this additive error is not uniquely determined for all the parties. So actually, we cannot use this. So the next option was the Dunbar-Nielsen protocol. So this is a 2-round protocol. Also, we have to generate some randomness that is input independent. But essentially what happens is that, again, the parties will reach a step where they have a sharing of degree 2t that they want to reduce to degree t. And here there is a central party called the king, and all the parties will send their shares to this king, and the king will then reconstruct the value and reshare it. However, there is a known attack for this protocol in the strong honest majority setting. And actually the king, if there is a strong honest majority, the king can recover the secret shares of the other parties. So this is not secure, and we cannot use it as well. Now, what we can use is the 1-round version of the Dunbar-Nielsen multiplication protocol. So in this protocol, instead of having one party play the king, it's as if every party is the king. So all the parties reveal their shares to everyone else, and everyone else will reconstruct this value. And this has the advantage of having only 1 round, but usually it is more expensive in terms of communication. However, in our case, broadcast is actually cheaper than point-to-point communication, which means that actually this protocol is even cheaper in terms of communication than the previous one. So what we do is that we use this protocol, we broadcast in our final protocol, and this is the final piece of our MPC protocol. Okay, then we also implemented our MPC protocol to check if it is indeed efficient. And the first thing we wanted to check is the overhead that is introduced by using relays for the communication. So we did several experiments. I will show you some of them. So we did some experiments where we sent an increasing number of messages, and this graph is a logarithmic scale. So we did this in different ways. So first, we use the relays first, never erasing any messages. So we always send, but they are never erased. Then in the second experiment, E1, we erase every message after retrieval. And finally, we erase messages in batches. And then we compare this with the DP experiment, which is communication without the relays as usual. And in fact, up to around this point of 2 to the 15 messages, everything is quite similar. But then the experiments E0 and E1, they start getting noticeably slower. And this is because, well, if we are constantly asking the relays to erase messages after each request, then it means we have a lot of communication with the relays. So that's why it gets slower quickly. But also, if we never erase messages, then at some point the relays have a huge number of messages. And so when we do a request, the relays have to look through a bunch of messages to figure out which is the right one. So the better idea is to erase messages in batches, because then we have a relatively small overhead when compared to communication without relays. And finally, we also do a last experiment where we communicate with relays and also for larger messages. So here we increase the size of the messages, and they are 1,000 times larger than previously. And we also see that there's not a significant overhead that is added while adding this size of the messages. Then we did exactly the same experiments for broadcast, and well, actually, the experiments are inherently different because before there's one sender and one receiver, while here every party is both a sender and a receiver. So it's hard to compare both. And in fact, here we don't have the same thing we had before, where the E0 and E1 experiment gets slower. And this is because the way the implementation is done, the way the messages are stored for broadcast is different than for point-to-point communication. So maybe, in fact, we could improve the point-to-point communication implementation in order to have something like this. But in any case, the better idea is always to erase messages in batches in order to avoid the relays running out of space. Okay, so finally, we also did experiments for the MPC protocol itself. And the way we did it is by increasing the number of batch multiplications in each round, and then seeing how many multiplications per second we can do. And we did this both with 3 parties and with 6 parties. And in the 6-party case, we have 3 parties that run in faster computers than the other 3. And this is sort of to simulate the effect of having relays. And indeed, what we can see is that the 3 fast parties in the 6-party protocol, they do approximately the same number of multiplications per second as the 3 parties in the 3-party protocol. While the 3 slower parties, they are noticeably slower. And for the larger number of batched messages, that we can do around 270K multiplications per second. And this is not a specially optimized implementation. So we estimate that if we were to optimize our implementation, then we could probably get something around a few millions of multiplications per second. Okay, just to conclude, what we did was we presented an MPC protocol that uses relays for communication, and we proved that it is secure even in the presence of delays. We also discuss how to do multiplication in this setting, and finally, we show some experimental results for the efficiency of this protocol. Then there are a few things not in the paper, that not in the presentation, but also in the paper, such as how to do key agreement. We also discuss how the size of the states stored in the relays increases for different situations. And finally, we also discuss some possible optimizations in terms of non-complexity or
Okay, thank you for the talk. Any questions? Thanks. Excellent work. I have noticed that your technical adopts ideas of greater MPC, such as the mass. Yes, this means support a dishonest majority. My question is, what's the difference between honest majority setting and dishonest majority setting in this star-like network? Does this a difference from that in traditional networks?
So you asked about the difference between honest majority and dishonest majority.
Yeah, it or star-like.
Yeah. So in our case, it's so if we were to have a dishonest majority, then we could not have this thing where faster parties move ahead in the computation. So, I mean, I guess we could still, then delays would be noticeable. So I think the good thing in our protocol is that even if parties are delayed, then the others don't have to wait. So it's still fast. But if we cannot do this, then this moving ahead is not possible. So I would say there's not that much gain in, I mean, having the relays for message storage is still interesting because it allows dropouts, but it's not the same thing if we cannot.
So it's open session. Thank you.
Okay, so can we achieve better results if we relax the assumptions on the corruptions of the relays? You just assume the corruption of the relays is an all but one corruption. Can we relax it to get some stronger or better results?
Yeah, so for example, in this case, if we detect that not all messages that the relays send, if not all of them are the same, then we know, oh, some of them are corrupted and we abort. But if we have, for example, an honest majority of relays, then we can still detect, okay, what is the correct message? And then we can even detect which are the malicious relays. So yeah, and probably there are even more properties there.
So maybe we can achieve like guaranteed output.
Yeah, I'm not sure, but yeah, it could be interesting to look into more possibilities.
Or can can we achieve some better efficiency or achieve or the honest parties the fast parties can proceed more rounds than the slower parties?
Yeah, so I think indeed, if we have more honest relays, then if we maybe don't even have to wait for all the relays to reply, and then maybe we can.
Thank you.
Any more questions?
Thank you for your talk. I have a question. Could we treat the relay and router?
Relay, I see.
Router.
Yeah, I mean, I guess we could, but then, so you mean that they don't store anything?
I'm not sure.
Yeah, I'm not sure what that exactly means.
If I think, yes, if the router or if the relayer they don't store anything, just return the sorry. They just relay the information. The protocol is secure.
Yeah, I mean, I guess you can have something secure, but then it's different. I think it would be really like all the properties of the delays and all that. It relies on the fact that the delays store messages. So I guess if they don't store anything, then yeah, it's not the same thing.
Thank you.
Any more questions?
If we use two relays, the latency will be increased the latency.
Yeah, I mean, so when we have relay, it's just because. So the relays don't send the message
From the sender to relay
Yeah.
and from the relay to receiver.
Yeah,
It
there's
will be
always
double.
yeah, there is an increase in latency. For sure. So that's what we actually in the first group of experiments I showed. That's what we are trying to test because we know we will increase latency. Yeah, but we gain other properties.
If a attacker always attack one relay to make the two messages from two relay is not equal, so it can attack the whole system, right?
Okay, I think okay, one more.
Yeah,
One more question. Okay, thank you.
I wonder that in your work, you're considering about the passive security, right?
Then at the end we can actually obtain active security. So
Okay, and can we make a stronger assumption that we require more honest parties to achieve a high level security that achieved in Byzantine fault tolerance protocols?
yeah, so I'm not too sure. So in the end, what we get is active security with the BART. But yeah, maybe if we have the different assumptions, we can get some stronger notions. But yeah, we have not discussed that. But yeah, thank you. It's an interesting question.
Okay, let's thank the speaker again. I think that's the end of the section. Let's thank all the speakers. We are going to have an IACR membership meeting in Bristol Ballroom if you are interested to join. Otherwise, I see you at the banquet tonight. Thank you.